Hi, welcome to this video. So what is this video talking about? As what the title say, it's a CCNA class. So what does it mean? I recommend you to watch this video before you attend the actual CCNA class. As a Cisco certified instructor for over 2 decades, I have taught many CCNA classes. Although CCNA is supposed to be an introductory course, nowadays Cisco puts so many information into the CCNA course. So without any basic knowledge, I am sure that you will not be able to catch up in the class. So I create this video to help you understanding how the network works, how the switch and the routers forward the message within the network. Even though if you don't have any planning to take the CCNA class, if you are an IT guy, no matter whether you are server support, a developer, it is also a good video to give you some idea about how the network works. Because undoubtedly, networking is one of the most important technologies in the IT world. Here is a little bit about myself. I teach many different Cisco courses. Besides CCNA, I also teach CCNP, security check, like those ASA, collaboration, for example, call manager, Unity servers. Recent years, I also teach data center technologies, like those Nexus switch, ACI. Currently, I'm an individual consultant, doing like those network design and plannings, migration and security assessment. I also develop open source software. Besides teaching Cisco, I'm also a certified instructor for some other vendors, something like Juniper, H3C, F5. If you want to know more about me, take a look on my personal blog. Feel free to leave me some comment. Here is what we are going to discuss in this presentation. I'll first review the functions of the network. The network address will focus on the IP address, discuss about like subnet mask, prefix length, and so on. And then I will expand what's the roles of the switch and the routers in the network. And then finally, the most important part is to expand how the message is being carried from the sender node to the destination node over the whole network. If you are a newcomer in the networking, I recommend you to go through all the slides. But if you're already working in networking field for a period of time, you believe that you know what those IP address, subnet mask, and so on, you can try directly jump to the last part, which start on slide 13. Before we discuss how the network works, maybe one of the questions is, what's the purpose or the functions of the network? Now maybe the simple answer is, it enables the communications. Yes, it enables communications. But for whom? For human beings? Are human beings the direct users of the network? That is one of the questions I like to ask in my class. Does your body has a leg card that can plug into the network? Obviously not, right? So to access the network, usually you need to have some sort of network interface. Usually only those computer equipments, something like PCs, servers, printers, IP phones, and so on, they have the network interface that can plug into the network. That means the network enables communication between those computer equipments. We refer them as the network nodes. More precisely, the network enables the communication between the applications running on the network nodes. To understanding how the network works, maybe the first thing to discuss is about the network address. In fact, the network is somewhat like our mailing system. It just carries message between those network nodes. In order to receive a message, every looks must have an address. It's just like the mailing address of your home. This address must have an agreed format. It depends on the network protocol. So what is protocol? We are going to discuss it in the coming slide. Nowadays, the most commonly used protocol is the IP. For the IP address, we have a 4 bytes or 32 bits entity. You may always heard from the networking guys talking about protocols. Now what is protocols? Protocol defines a set of rules that govern the communication procedure. For example, when a client needs to communicate with the server, it needs to send some kinds of fixed format message to the server. Similarly, the server also needs to reply with certain kinds of message. Think about just like a phone call. When you pick up the call, what will you say? You will say hello, right? And the other end also reply with an hello. So this is a kind of protocol, somewhat like a handshake. Protocol also defines the address format. As mentioned in the previous slide, nowadays the most commonly used protocol is the Internet Protocol, IP. The version we are still using is called the v4, which is actually the CCNA focus. Some people may already heard about that. Over 10 years ago, the internet is already out of v4 address. So people already developed a newer version, which is called the version 6. Version 6 has a longer address format. There are some other, I call it vendor-specific protocol, like the SNA from IBM, OSI originally from Digital Equipment. Those are not commonly being used nowadays. Now I'll focus a little bit about the v4 address. As discussed before, the v4 address consists of 4 different bytes. Each byte is separated by a dot. And the v4 address usually we represent each byte by a decimal number. So I'm assuming that you know what is 1 byte. In decimal, 1 byte can be ranges from 0 to 255. That means the x in here, each x can be in the ranges from 0 to 255. So here are some of the examples of a valid v4 address. While the lower part indicates some invalid address, like the first one, 10.256. 256 is out of the range. And the second example only gets 3 different bytes, while the last one gets 5 bytes. Right? So they are not the valid v4 address. Now, let's take a more detailed look in the IP address. Actually, the IP address consists of 2 different parts. The first part is called the network number, while the second part is called the host part. For the network part, sometimes you also refer it as a network prefix or subnet prefix. Like for example, 10.2.138.5, I can select 2 bytes as the network part, while the second example in here, 10.10.1.128, I can use the first 3 bytes as the network number, and then the last byte, 128, as the host part. Then you may have questions. How can I know how long is the network part and how long is the host part? The answer is it's user definable. Usually it's chosen by the network designer. But then you may have another question. If somebody gives me an IP address, how can I know which part is the network number, which part is the host number? The answer is we will use what we call a subnet mask, or what we use another notation which is called the prefix length. Like the first example in here, if I choose 2 bytes 10.2 as the network number. So for 2 bytes, how many bits are there? Once again, I'm assuming that you know what is 1 byte. 1 byte consists of 8 bits, right? So for 2 bytes, actually is 16 bits. So we use /16. That means the first 16 bits, 10.2 in here, is the network number. While the second example in here, 10.10.1, I choose it as the network prefix, right? So 3 bytes. So once again, how many bits are for 3 bytes? For 3 bytes, you get 24 bits, right? Then we use /24 to represent the first 24 bits are the network numbers. The second method is the subnet mask. In order to understanding the subnet mask, you need to have some knowledge about the binary numbers, which I don't want to go too depth in it because you will learn it in the CCNA class. Just use the example. Say if I use 16 bits as the network number, then if I express the subnet mask in binary format, then I will use 16 ones to indicate the network part, while I will use 16 zeros to represent the host part. But is it too clumsy to write down so many zeros and ones? So we convert it back to decimal. How to do it? We group 8 different bits back to 1 byte. That means 98 ones. If we convert it back to the decimal, it will becoming 255. So for 16 ones, actually it will becoming 255.255. For the last 16 zeros, alphas it becoming 0.0. Then what about for 24 bits prefix? 24 is actually 3 sets of 8 bits, right? So for every these 8 different ones, once again becoming 255. So it becoming 255.255.255.0. Before we move on to the discussion of router and switch, we discuss one of the important concepts, which is called the network segment. Remember that in the IP address, one part of it is the network number. Network number is somewhat like the regions of a mailing address. It's saying that one segment consists of all the looks or devices that have the same network number. That means if 2 looks they have the same network number, we say that they are on the same segment. So here 10.1.1.10/24 and 10.1.100/24, because the first 24 bits, that is the network numbers, are the same, right? So these 2 IP addresses are on the same segments. Usually we set the host part to be 0 to represent the whole segment. That is in this case 10.1.1.0/24 represent the whole segments. So the second example in here, 10.1.2.10/24 and 10.1.3.10/24, are they on the same segment? The answer is no, right? Because the network number is not the same. Actually, the network segment is a very important concept. Why is it? Because the whole networks are actually built by connecting many different network segments. Another question is that how large is one network segment? That means how many IP addresses can be put in one network segment? Now maybe you already know the answer. Actually, depending on how long is the host part, right? If the host part getting more bits, then the network segment can be larger, right? Now we move on to the network device. So what are the network device? Actually, the whole network is formed by the network device, right? And the function of the network device is to carry the message over the network. There are two major components which are actually the CCNA focus. One of it is the router, the other is the switch. But what's the difference between the router and the switch? Router can carry the message over different segments. That means from one segment to another segment and so on. While the switch can carry message within the same segment. There are some other network devices like firewall, VPN server, IPS. Those devices are more related with the security control. They are not the CCNA focus. Now, routers. So routers connect different segments in the networks. As discussed in the previous slide, routers can carry the message from one segment to another segment and so on. So it's just like a postman. So router actually forward the message based on the destination IP address. The network works just like a traditional mailing system. When a sender looks want to send something to the destination log, it will mark the message with the destination IP address, and then it will send it to the nearest router. Usually we refer this nearest router as the default gateway of the sender log. When this first router receives the message, it will look up a table which we call it the routing table. I will discuss more detail in some coming slides about the routing table. The purpose of the routing tables is to find out what should be the outgoing interface, or what should be the next router the message to forward, and then it will forward it. Once the next router receives it, it do the similar things, and then this process will continue and continue until the message reaches the last router, and then the last router will directly deliver the message to the destination log. Then what about the switch? As discussed before, switch different from the router that switch can only carry message within the same segment. That means switch can only carry message between two logs. They have the same network number. Like the diagram in here, all the PCs are on the network number 10.10.1. In fact, switch doesn't make use of the IP address. Instead, the switch has another table we call the MAC address table. It's based on another address which we call the hardware address, or sometimes MAC address. Don't worry about it, we will discuss more details in some coming slides. Now I will go more detail to discuss how can a message be carried over the network from the sender log to the destination log. I will use this simple network to explain the whole process. Let's take a look on this network. The first thing you want to check out is about how many different network segments are in this network. To answer these questions, you just need to check how many different network numbers are in there, right? Now let's take a look on the left hand side. You have 10.10.1, which is a 24-bit network prefix, right? Okay, so this is the first segment. While in the middle one, you have 10.10.3, and on your right hand side, you have the 10.10.2. That means we have 3 different segments in here. What I want to discuss is that the web browsers on PC1 want to communicate with the web server on the right hand side. The web server has the IP address 10.10.2.1. Right? Before we discuss how the message are being carried over the network, let's take a look on what to be configured first. For all the PCs and the servers, you need to configure their own IP address and the corresponding subnet mask. Besides that, you also need to configure the default gateway. Remember that what is the default gateway, which is the closest routers for that particular device. For example, on PC1, the default gateway is 10.10.1.254. And also you need to configure the DNS server's IP address. Don't worry about it first. I will discuss it in the coming slide about the DNS server. Then what about the routers? Remember that routers connect multiple segments. It uses different interfaces to connect different segments. That means for every different interface, it has its own IP address and the corresponding subnet mask to be configured. Like in here, for example, for R1, actually you need to configure two different IP addresses. One is on the E0, which is 10.10.1.254, and the corresponding subnet mask is 255.255.255.0. Besides that, you also need to configure the E1, which has another IP address 10.10.3.1. In order to maintain the routing table, you must either enable routing protocol, or you can use the static route. In this presentation, I will not go so detailed about those, because you will learn it in the actual CCNA class. It may span like 2 days or even more. That is one of the major topics in the CCNA class. Lastly, switches. It may be a little surprised that you doesn't need to configure anything on the switch. Or you may wonder, because maybe some of the networking guys tell you that you need to configure the IP address and even the routing protocols on the switch. Why is it? Because nowadays, some of the switch also integrate the functions of the routers. We refer it as the multi-layer switch. But in this presentation, I'm talking about the traditional switch, or we call it the layer 2 switch. Now we go to the whole process. The first step is that for the PC1, you need to figure out the IP address of the web server. Think about in your browser. Do you enter the IP address of the web server, or do you use the name of the web server? Usually we use the name, right? Something like www.googles.com. But unfortunately, the network doesn't use the name. Instead, the network requires the destination IP address. That means PC1 need to resolve the IP address of the web server. How can it do it? The answer is the DNS server. I believe most of the people already know what is a DNS server doing. In fact, the DNS system is somewhat like a distributed database system. Usually, it's not only just one single server. It's a set of servers. Of course, the DNS architecture is out of our discussion here. All you need to know is that the DNS server provides a mapping of those host name to its corresponding IP address. So now PC1 will send a query to the DNS server, and the DNS server will reply the IP address of the web server. The way that PC1 communicates with the DNS server is exactly the way that it communicates with the IP address of the web server, which we are going to discuss. That is start from the step 2. So after getting the reply from the DNS server, right now the PC1 knowing that the destination IP address, that is the IP address of the web server, is 10.10.2.1. Now the next step is PC1 will need to determine whether the destination IP and itself are they on the same segment, because the treatment is different. If somebody notices one of my previous slide, it's saying that if I send something to the same segment, do I need a router? The answer is no, right? if I want to send it to another segment, then actually I need to send to the router. That is the default gateway. I will explain in more detail in the coming slide. To send something over the same segment, actually we don't require the IP address. Instead, we require another address we call the Ethernet address. Maybe that is one of the most puzzling things why we require two different addresses. It's a little bit historical reason, because in the old time, networks may only consist of one single segment. In this case, we can just use the Ethernet address to communicate. So what is a Ethernet address? Ethernet address sometimes we refer as a hardware address, burn-in address, or MAC address. In fact, precisely, those different names has a little bit different meaning, but don't make it so complicated. Just treat it the same in here. So for every NIC card, it already comes with this address. That means in the world, every NIC card has a unique Ethernet address. This address has 6 bytes. We represent every byte using a hexadecimal and then separated by a colon. For Windows, it like to use hyphen to separate each byte. In fact, the switch will forward the message based on this hardware address. In the switch, there is a table we call the MAC address table. The switch will try to learn all the hardware address of the attached logs. For example, it will try to learn PC1's hardware address and is learned on its interface Ethernet 1. Similarly, it will also learn the hardware address of Ethernet 0 of R1, which will be learned on the Ethernet 2 of the switch. Remember that I mentioned that the switch doesn't require to be configured, even for this MAC address table, because the switch has the intelligence to learn those MAC address. I will not spend time to expand the learning process in here, because you will learn it in more detail when you attend the CCNA class. We return back to the PC1. Now PC1 finding that the destination IP address and itself has a different network number. That means the destination IP address is on another segment. Then the message is required to send to the default gateway first. As the default gateway IP address and PC1 are on the same segment, that means PC1 can actually send to the hardware address of the default gateway. But wait a minute, does PC1 knows the hardware address of the default gateway? Have we configured the default gateway's hardware address in PC1? The answer is no. We just configure the default gateway IP address. Then the problem is, how can PC1 knows the hardware address of the default gateway? The answer is PC1 uses a protocol called ARP, Address Resolution Protocol. The purpose of the ARP is to find out the MAC address or the hardware address of a particular IP address. How it works is that it's just a query and a reply. The query is a broadcast message which is sending down to the switch. When the switch receives this broadcast message, it will replicate it to all the outgoing interface. That means the whole segment will receive this broadcast message. This query message simply asks, to guess the IP address that I want to resolve, please answer me with your hardware address. That means in this example, it asks, if you are 10.10.1.254, please answer me with your MAC address. Although this query is a broadcast message, that means all the logs in this local segment will receive it, but only R1 will answer it because R1 gets 10.10.1.254. So R1 will reply to PC1, here is my hardware address. The replied information will be cached for future use. What about if the destination and the source are in the same segment? I believe some of you are smart enough to answer these questions. In such case, the ARP is used directly to query the hardware address of the destination log instead of the default gateway. At this moment, PC1 gets enough information to send down the message to the lake card. It will attach this information to the message. This is called the encapsulation process. This information, including the destination hardware address, which is the hardware address of the default gateway. This information is put under what we call a Ethernet header. Besides that, it also includes the destination IP address. Notice that the destination IP address is the web server's IP. It's not the default gateway's IP address, because the final destination of this message is the web server. The message is then sent down to the lake card of the PC to the switch. When the switch receives it, it looks up its MAC address table. According to the destination hardware address, the switch will determine which outgoing interface this message should forward to. In this example, it will forward to its interface Ethernet 2. Now it comes to the router. When router R1 receives the message from the switch, it will discard the Ethernet header. Remember that because the router doesn't make use of the hardware address for the forwarding decision. Instead, it uses the destination IP address. Router has a routing table. It is not like the MAC address table. The router will not learn the IP address individually one by one. Instead, router will just only learn the network prefix. Moreover, router has a global view. It means that the router will try to learn all the network prefix of the whole network. Like in this example. Once again, how many different network numbers are there? There are 3, right? That means in the routing tables of R1, there should be 3 different entries. And then for every entry, there is an outgoing interface for forwarding the message to that particular destination. Depending on whether the destination is directly attached or not, there will be one more information. If the destination is not directly connected, the router will need to forward the message to the other router. This is called the next hop routers. Like in here, if R1 needs to forward a packet to 10.10.2.0, it needs to go through R2. And as R1 is connected to the interface E1 of R2, that means the next hop address is actually the IP address of this interface. So R1 will forward the message, or we call the packet, to this next hop address. Just like how PC1 sent this packet to R1. R1 will also require to resolve the hardware address of this next hop address. Some people may wonder, can I just send out the packet without those hardware address information? The answer is no, because the packet is handled by the lake card. The lake card requires those Ethernet address information. So once again, ARP is being used. R1 will send a query to R2 to query its hardware address of interface E1. So after receive the reply, R1 will use this information to rebuild a new Ethernet header with the corresponding destination hardware address, and then it will send out the message through its interface E1. There may be one more question. How does the router maintain the routing information? As mentioned before in one of my slides, you can either use the static route. That means you enter those routing information manually. However, nowadays networks are too complicated. It is almost impossible to manually maintain the routing information. Then usually we will enable the routing protocol. In short, routing protocols allow the routers to exchange the routing information among themselves so that they can learn the remote prefix of the whole network. Now, how to receive the packets from R1. Just like what R1 does, R2 discards the Ethernet header of the packet, and then it will look up the destination IP address of the packets against the routing table. R2 has a similar routing table as R1, but obviously the outgoing interface of those destinations will be different. Like for the network number 10.10.2.0, for R2 this network number is directly attached. That means there is no next hop information. Instead, R2 can directly send out the packet through its interface E0. Now, as the destination IP address 10.10.2.1 and the IP address of Ethernet 0 of R2 are on the same segment, that means once again, R2 can send to the hardware address of the destination IP address. I believe most of you can already deduce that once again, ARP is being used to find out the destination hardware address. So after getting the hardware address of 10.10.2.1, R2 rebuild the new Ethernet header and then send down the packet through its interface E0. We're almost done. So the packet arrives switch 2 from the router. Just like what switch 1's doing. Switch 2 look up the destination MAC address against its MAC address table to find out the outgoing interface. The outgoing interface of this example is the E2. So the switch sends down the message to this interface. Finally, the destination server receives it. So we are done. To conclude what we have learned in this presentation, the network consists of two levels of equipment. One is the switch, the other is the router. Switch only forward message within the same segment. It has a MAC address table. It forwards the message based on the destination MAC address of the message. While routers can forward message across different segments, it forwards the message based on the destination IP address of the packet. It has a global view. It means that routers should know all the destination network numbers of the whole network, and it will learn all those in its routing table. Lastly, we discussed the ARP, Address Resolution Protocol, which is used to resolve the hardware address from the IP address. Thanks for watching. I wish you liked this video. If so, please give me a like. This is my first video on CCNA. Although I don't have a plan to present the whole course, I will select some of the most confusing and difficult topics to be presented in future videos. Something like spelling tree, subnet mask. So, if you want to follow what I will be doing in the future videos, please subscribe this channel. Once again, thanks for watching. Goodbye.